Shall we start, Mukesh?
Yes, sir, I'm ready.
Yeah. Good afternoon to everyone. I welcome all of you to the 20th lecture in the lecture series in nonlinear dynamics conducted by Department of Nonlinear Dynamics, Bharathasan University. I'm happy to introduce today's speaker, Professor Murugesh from Indian Institute of Space Science and Technology, Thiruvananthapuram, to you. Professor Murugesh is a well-known person to our department, and in fact is a friend of mine. In view of MSc students, I wish to read out Professor Murugesh's biodata in a very brief manner. Professor Murugesh did his MSc in Madurai Kamaraj University, Madurai, and completed his PhD in the Institute of Mathematical Sciences, Chennai, which is one of the premier institutes sponsored by DAE. And then he served as a research associate in our department. And then he carried out his postdoctoral studies in the School of Mathematics, University of New South Wales, Sydney, Australia. After a couple of years, he came back to India and joined as a scientist in our department. Then he joined as an assistant professor in the Department of Physics and Meteorology, IIT Kharagpur, before joining in the Institute of Space Science and Technology. As far as research is concerned, Professor Murugesh is working on integrable systems, and he is studying the integrability properties mathematically and physically. He is also studying the applications of solitons in condensed matter physics. And if you want to know more about him, please visit his homepage. So with this short introduction, now I hand over the session to Professor Murugesh. Over to you, Murugesh.
Yes, sir. Thank you, sir, and very good afternoon to all of you. It is very nice connecting back to the department where I have spent a very critical phase through my career. So in spite of going through this pandemic, I think we should thank the pandemic, because I don't think this kind of an elaborate set of lectures could have been arranged by any university for that matter in real time on offline mode. You could not have collected so many people coming to a place because this already, I see that this is 20 lectures have happened from very active people. That could not have been possible with offline. So probably pandemic is bringing some more activity there. I will briefly mention about the institute where I'm currently working before I start my talk. And we'll share the screen, but the first screen is simply there. Yeah, so this is a topic I'm going to be talking about. But before that, I'll say something about this institution. This is Indian Institute of Space Science and Technology, which is in Trivandrum. It was started in the year 2007. With the intention, it was funded by the Department of Space, with the intention of having a close association with ISRO and its research activities. There is substantial amount of research that is happening, which is directly into ISRO's requirements. Yesterday, it was a very good day because the first satellite from our institute was launched in the PSLV that was launched yesterday successfully. The institute is located in Trivandrum, I told you. We primarily offer 3 undergraduate programs. One is in aerospace engineering, electronics and communication engineering. And third, there is a dual degree program, which is engineering physics, leading to a dual degree in either a Master of Science or a MTech. There are 4 options there: optical engineering, astronomy and astrophysics, solid-state physics, and atmospheric sciences. There are a few other engineering master's program also that are offered by the aerospace as well as EC avionics departments. And we also have a PhD program. So the intake is post-MSc typically for many of these MTech programs as well as MS programs and PhD. And I'll be glad if some of you are motivated enough to try out the admission process in our institute. Okay. So now I will go over to my talk. So the title is Breather Modes and Spin Systems. I will particularly focus on some certain breather modes, and we have found that there is something interesting geometrically that is happening there, intriguing as well as interesting. And so that is what mostly I'll be focusing on. But at the outset, I will also express my discomfort in giving this talk here because, uh, firstly, I'm not a stranger to the department, and this activity, what I'm going to talk about, significantly is happening in BDU. I know this very well. Okay. In fact, I myself started much of this work when I was there. So this is the broad outline of my talk, and okay, first a second, yeah. This is about, first I'll start saying something about the spin magnetic moments. It's what is its nature? What do we mean when we say that it is spin? And I'll give a perspective on what are the applications, what is really driving this field. There are a lot of applications already, and more applications are expected to happen soon. Some of them are in prototypes. Some of them have come out of the labs. Some of them have reached the industry level. We expect to see some major change in our applications, day-to-day applications, very soon. Okay, so I will give a motivation for this. It is also the reason why many people are interested in this subject these days. And finally, I will focus on what I call as a rogue breather in spin modes. And this bell trick is the geometric phenomenon that I was talking about. It's a very curious maneuver. Most of my time I'll be discussing on this, and keeping in mind that there is a large section of students involved, most of it will be focused pedagogically. So I know that people who are already in research at BDU and elsewhere might find many of these things trivial, but I will go through them nevertheless with the intention of conveying it to the students who are attending. Okay? And all the results that I am going to be talking about can be found in these two papers. So what is the spin magnetic moment? We represent it by a vector quantity S. Okay, and it's a vector quantity. It is quantum in nature. Now here is a small picture, which is actually a wrong picture. The best picture that you can get is something like this, where this is supposed to represent an electron. They have given north and south in this indication, but it's to say that there is a vector which has two directions associated there. It is directed. The main problem with this picture, why I'm saying that this is a wrong picture, is that it is given with this arrow, right, going around it. It gives an impression that it is something that is spinning, and the name also gives you the same impression, but the truth is the electron does not spin. That's not why it is called as a spin. So just as the electron has a charge, a mass, it also has a spin magnetic moment. So the nomenclature is driven by our classical understanding of magnetic moments, because the magnetic moment is associated with a loop of current. So that is probably why people named it as spin, but truly it is not like the electron is spinning. It is just like one of the properties of electrons. Along with mass and charge, it also has a spin magnetic moment. It is quantum in nature, and also there is relativity involved. In order to be consistent with relativity, quantum mechanics says that the electron must possess a spin, otherwise it is not possible. Yeah. So we have throughout, when I'm going to be talking about spins here, I want you to keep in mind what is the actual system that I'm talking about. So to understand that, you should know that the spin magnetic moment of a particle is inversely proportional to the mass. So when I'm talking about spin of what that I'm talking about. So if I take an atom, for example, the proton has a magnetic moment, the electron also has a magnetic moment. But then the magnetic moment is inversely proportional to the mass, and the mass of the proton is like 10,000 times that of the electron, which means the magnetic moment of the proton or the nucleus, no matter which atom you're talking about, is going to be like 1 by 10,000 of the spin magnetic moment. So the spin magnetic moment contribution mainly comes from the electron. Its magnitude is a constant. And you know that in an atom, electrons tend to pair up, right? There is this Pauli's exclusion principle which tells you that electrons will pair up. So when I say that the spin of an atom, I have already ruled out the contribution from the nucleus, because the nucleus spin magnetic moment is very small. It's 1 over 10,000 of the spin due to the electron. And out of all possible electrons, you are going to have that the paired electrons will not contribute because they will have opposite direction spin magnetic moment. So Usually the spin magnetic moment is associated with the atom, but that is mainly coming from a one electron which is unpaired somewhere. So even though we talk about the spin magnetic moment of an electron, what we have in mind is actually an atom, but the contribution for spin magnetic moment actually comes from one electron at most. Okay. And what you are seeing in the next picture is like a domain. So we are not just talking about a single atom. We talk about a piece of magnetic material. And magnetic material, there are domains. There are regions where magnetization will be aligned in some direction. And when you say that the system has a magnetization, it is like on an average, there is some non-zero direction in which there is a magnetization. So this helps us often to deal with the magnetization as a classical quantity, because now I'm going to be talking about the average magnetization of this small piece of magnet. So I want you to understand this. So when I'm going to be talking about spin magnetic moment and its dynamics from now on, the S actually is a vector quantity, but then what I'll be representing as S is actually the average magnetization due to all the atoms in the magnetic domain. And as the spin or the number of electrons I'm going to be talking about becomes larger, the average value starts behaving like a classical quantity. So to a good extent, we can treat them as a classical object. That means it can take continuous values. Yeah, so it can be treated as a continuous values. So what are the kind of interactions that the spins go through? Firstly, there is this exchange interaction. The exchange interaction is a very curious interaction. It has a quantum nature. Its origin is quantum. It's again coming from the Pauli's exclusion principle. It is diverse in the sense that depending on the material, it can lead to ferromagnetism or antiferromagnetism or other aspects. It can also have a dipole-dipole interaction between two adjacent spins, but usually this is too weak compared to exchange interaction. So we normally deal only with exchange interaction. When exchange interaction is present, the dipole interaction is too small, okay, to be discussed about. The dipole interaction is a classical origin. Like if you have two loops of current, then they like to be oriented in the same direction. Likewise, two spin magnetic moments will also like to be oriented in the same direction. Now, how do we manipulate it? The exchange and dipole interactions I told you about are properties associated with the material. But if I want to do some applications or play around with it, I need to be able to control something externally in the lab. How can I control it? One way is to apply a magnetic field. The magnetic field will control the spin. You can also apply a polarized current. Okay, a polarized current is a current where the electrons usually have their spin in some particular direction. Okay. So there is an average orientation for the spins, which is non-zero for a current. A normal current is unpolarized in the sense that you have spins in the electrons oriented in random directions. But a spin polarized current is where like nearly 40% or 30% of the electrons are polarized. I am not going to be talking about manipulation in this lecture. That is for application point of view. But it is important to understand what all we can do with the subject. Yeah, so now this is a detour. It's not really important for the rest of my talk, but I thought I'll give like I said, I'll give a perspective on what is really driving this area of research. So from the application point of view, what is really the importance and people are concerned about. So you must have heard about this Moore's law. It's not actually a law. It is just some observation he made in some, this gentleman made in some journal. It was not stated as a law, but it has remained as a law. The statement was that the density of transistors on chips doubles every year. It was like a comment without any scientific basis, but just a feeling that he had looking at how the technology was developing. And strangely, it has been behaving in that manner. So for example, this is 1970, okay, a little before this suggestion was made. So you can see that it is like what it gives you is number of transistors that can be packed in 1 centimeter square. So here it is like 1000 transistors, and you see in the close to 2016 or even here like around 2000. Okay, what is this? This is 2012 or something. It has already reached 1 billion. So the numbers are increasing. The size of the transistor becomes smaller and smaller. And that, okay, this again gives the progression. So in 71, it is like 500 transistors per centimeter square. And then it is going into billions. Now that poses a problem because there are two different directions the problem leads to, because when you make it smaller and smaller, beyond a stage we cannot use it anymore, because it is not classical physics that governs the behavior once you take your transistor size to below nanometers. Quantum features will start coming in. What do I mean by classical feature there is, if I take a gate, for example, every gate has a truth table. Now the truth table must be repeatable. Okay? If I have 0, 0, what is the output? 0, 1, what is the output? Etc. etc. If I repeat that, I should get the same result. That is the way our classical computer works. The flip-flop that you are using in your laptop, every time you give the same input, it should give you the same output. Whereas, in a quantum system, that is not how things work. For the same input, you can get different outputs. All we can tell about is the probability of the outcome. That starts happening once the transistor becomes smaller than this size, and we are already hitting that size. So now the kind of transistors we are using, it's reaching a point where we cannot use it anymore to do the kind of computing we are doing. There's some more years maybe. So there is end of classical computing. So one possibility is that we go to quantum computing, and quantum computing is another story for a different day. It brings in a lot of possibilities. Things we cannot accomplish using classical computing can be done using quantum computing. But still there are, ironically, even though the quantum computer is very powerful, or will be very powerful once we have it, there are still problems like simple addition and subtraction, which is like, for instance, most of salary calculation or your supermarket calculations. There is a whole lot of calculations which involve simple calculations, but a large amount of them, which does not require quantum computing, but just normal classical computing. Okay? And for those, incidentally, quantum computer may not be such an effective tool. Okay? So that means classical computing still, the kind of problems we will be dealing in classical computing still exist, and for that, we still look for better candidates. So there are other issues that we can address. For example, volatility is one problem, right? I will explain that a little soon. And power consumption we try to reduce. In fact, these are some of the things that we have been trying to address by increasing the density of our transistor package. As the transistors became smaller and smaller, they became faster, they consume less power, etc., etc. But now we are hitting a threshold. But magnetization based applications, they bring in a completely different dimension to this application and this kind of power consumption. So these issues like mobility, speed, etc., these are the things that we would like to address. Now this is a cartoon of your regular RAM. Each of these are memory elements, and each memory element in effect is a transistor, and the transistor is charged. So if it holds a charge, we say that it is in state 0. If it does not, then probably we'll say that it is in state 1, just a convention. But this thing is volatile in the sense that to retain charge here, you should be supplying power. If you do not supply power even for a short duration, then that memory will be lost. This is something that you should be familiar with in your electronics lab. You can charge a capacitor, but if you leave it like that, soon it will die down. It cannot retain the charge forever. Right? So this is an issue of volatility. And this non-volatility, so these are different ways in which currently there are applications where one can address it. For example, BIOS in your computer, for which there is a separate battery that is used. You can have the solid state flash memories that you are using, like SSD cards, the kind of magnetic cards that you are using in, the kind of memory cards, solid state devices that you are using in your laptops or even your mobile phone. But those cannot be used as RAM, okay, for different reasons. One, the number of times you can read and write, that is limited in your SD card that you are using in your mobile phone. And some of these things you cannot specifically write one particular memory. You have to write it in a flash. That's why one used to call it as flash memory, because it's one entire page that is written. It's not specifically one address location where it is written. So every different variety of the solid state memory has its own issue. Okay? So these are things that you are already familiar with. right? All the SSD cards you must have seen, USB pen drives, etc., etc. Now the alternative is this, which is a magnetic memory. Okay, it's a magnetic RAM. The left hand side, it is just a magnetic RAM, and the right hand side, what you are seeing is a picture of a spin transfer torque magnetic RAM, which is more powerful. So here, what are we doing here? Your states 0 and 1 are going to be basically the spin orientations, either up or down, to give a very simple picture. Okay, what one uses as the transistor there or the flip-flop there is going to be a spin valve pillar. I will not go into the structure, but effectively it is like the spin orientation is going to determine whether it is in a state 0 or 1. An up state I will call as maybe 0, and a down state I will call it as a 1. The advantage with magnetic memory is that once I put it in a state, I don't have to keep supplying energy to keep it in that state, unlike the case of RAM. So your usual computer or laptop, for example, it consumes a lot of energy even for doing nothing because it is on. Just to retain that information in the RAM, etc., it has to be supplied energy. So there is a lot of consumption. Alternately, if I'm to use a magnetic memory, I can simply switch off the computer and turn it on. All the memory will be still there. So I can just start using it. So you can imagine the amount of power consumption that brings in. So that is primarily the direction in which uh, this entire field of magnetic RAMs is progressing. It's also the reason why many large companies, I have listed a few of them, there are more. All the big companies are investing in the subject to get it to the market. What you are seeing is not, okay, it is currently available in the market, but not to a size, right? This is like 16 MB, 1 GB. These are too small for things to be used in. So people use it in cache memory applications, etc., but not really as a RAM. It hasn't started yet. Okay. So what we have talked about here are single domain or average. There is one magnetization there. I won't go into the details of what I'm showing here. It is also possible that you can have an inhomogeneous magnetic domain where the inhomogeneity can have a structure, and that structure can also be manipulated and treated as memory element. So here, for example, I have a spin wave. What you see on the lower one is a kind of a vertex. Okay, this one on the top is what you call as a domain wall. Okay, there are two domains, one orientation to the left, the other one orientation to the right. Okay, this is right and this is left. In between there is a wall. You can manipulate the wall by application of a current or a magnetic field, and you can again make use of them as memory units with up or down. And there are a few more applications. Probably I'll skip. This is depending on the kind of geometry it has. It's the wall is designated different names. Okay, I'll skip this. Yeah, so this is another. It's a domain wall which is manipulated by means of a current. Okay, you can manipulate them by applying a current and have good control, which is helping in reading and writing. Okay. Now I'll go to the problem which I'm going to be talking about. So I told you about this Heisenberg interaction. This is the exchange interaction, the simplest caricature. So you see there is a minus J. J is taken to be positive in the case of ferromagnets. And this is a spin which is like a unit vector at the site I. And this is the next one is Si plus 1 is the spin magnetic moment at the site I plus 1. And their interaction is a dotted one. So that means it's given that this is negative, they would like to be in the same direction. Okay. So that is a primary tendency among the spins if this interaction were present. They will all like to be in the same direction, but it does have different features or dynamics that it can show. So there is this condition. I already told you that the spin magnetic moment, the magnitude is a constant. For convenience, I will take it as 1. It can always be scaled down to 1. One can rewrite this in the continuum limit because we will be treating in domains. I told you that this is an average spin magnetization that we are looking at. One can then look at the continuous value as the spin as a continuous variable, and here I'm looking at only a one-dimensional one. So the Hamiltonian or the energy can be written in this form. Now this you will recognize as something like the kinetic energy. Okay, so this is the kinetic energy of a free particle if you want. Since you must have done first course in quantum mechanics, you can recognize that this is like the kinetic energy and the kinetic energy of a free particle. So what is nonlinear here? The nonlinearity comes because of this constraint, because this S, if they were independent, S1, S2, S3, the components of spin, if they were independent, then this is a linear problem. But the problem is S1, S2, S3, the components, they are connected by this constraint, which is what actually brings the nonlinearity and also brings in all the geometry that is coming into the system. So once with this, I can look at how the things vary in time. This is called as a Baer-Lando Lipschitz equation. There are several features associated with the material I did not go through. Like for example, there is a anisotropy that is always present in the system. There is dissipation. There is a minor dissipation that is always there. Depending on of course, we are dealing with a one-dimensional case, but if I'm talking about a domain, depending on the shape of the material, there can be a demagnetization field that can actually take a very high value. But for my discussion, I will stick only to this part. The reason is that the exchange interaction alone, with the exchange interaction alone, this system is an integrable one. The integrability was shown by Professor Lakshmanan in 1977, and a little later by Takhtarjian in 1977. We will be heavily using this result. Now, I told you about the other effects like anisotropy, demagnetization, and damping. Normally, those things are dealt with numerically because it is very difficult to handle them at an analytical level. So what one does is one looks at the analytical results that can be obtained in the Baer model and then uses other studies to investigate how the behavior is going to change in presence of those effects. In particular, what I will be doing is I'm looking at the boundary condition, that is the spins at the two ends, they are frozen. So the spins in the intermediate one, they can change. And usually for low energy, it is a continuous transmission in the sense that the spins, adjacent spins, they will be differing only by a small amount. Now, this ribbon that I have shown is just a sample. It could be something different also. But the condition I'm going to impose is that the boundary spins, that is one at the extreme left and the one at the extreme right, they are frozen in the same direction as X. So the method that I am going to be following is the method of inverse scattering transform. There are different versions of this method. One of them I'll be using for my results here. So I'll give a quick summary of what the zero curvature condition, lag spare, and inverse scattering transform does, and how the whole thing is mechanized. This again, I believe many of you are familiar with, but I will give my own perspective of the whole thing. Okay. So this is a spin I'm dealing with. It has three components, S1, S2, S3. Of course, it depends on S. I have not shown there. It also depends on time. Now, what one does is one rewrites this as a matrix in this form. Sigma 1, sigma 2, sigma 3 are our regular Pauli matrices. Okay. So given any vector S, I will write a corresponding matrix which is like this. And I will bring in a fictitious function psi, which is also a matrix, such that this function's variation in Z is controlled by this kind of a potential L. Okay. So this is a linear equation, and for my purpose, the L is actually given like this. So you find that the L is dependent on S. Okay. The comparison is with our Schrodinger equation. In quantum mechanics, you know that this is a scattering equation. So the potential basically determines how my A is going to change in X. So in this fictitious problem, the psi is some fictitious wave, and the wave changes in the Z direction. And how it changes in the Z direction is controlled by this potential. The potential depends on S. Similarly, I will also imagine a time evolution for this wave, which is controlled by another potential, M, which again depends on S in some complicated manner. Now the wave depends on Z. Yeah, the Z subscript is actually the derivative. So that tells you how it varies in time and space. So if I can tell you how the two things are varying in space and time, then there has to be consistency because the derivatives have to commute. And that imposes a condition on the potentials L and M. This is what one calls as the zero curvature condition. Why do you call it as a zero curvature condition? Because there is a geometric meaning associated with that, but that I will not go through at the moment. Okay. And this equation, the zero curvature equation, is the same as the Lando-Lipschitz equation that I am going to be investigating. Okay. So in order to investigate this equation, we have rewritten them in this matrix form. And notice that one more important parameter, lambda, has been introduced, which is kind of arbitrary at the moment, but it plays a very important role. The simple statement is that if I have a nonlinear equation of this nature, if I can rewrite in this L and M potentials and this fictitious psi in that setting, then that system is integrable. How it is integrable once you rewrite in this form, again, I'm going to skip. But that is a theory. Once you manage to do that, I mean, how do you do that? There is no systematic way. It calls for a genius. So in many systems, we may be able to write. And that is the reason why integrable systems are very rare and they are very special. So not every nonlinear equation can be written in this LM setting. But this Heisenberg equation happens to be one such which can be done. Okay. And once I write it in this L and M form, okay, there is a lot of results I can systematically obtain, okay, which can give a good insight into the system as a whole. Yeah. So I just want to point out here that the L and M, they are matrices, of course, but they will be Lie algebra elements. I'm not sure if you are familiar with Lie algebras. But this at least you should be familiar. The psi that we are writing here, it will actually turn out to be a matrix. And that matrix is a SU2 matrix. What is an SU2 matrix? Again, I will explain a little later. Why I am pointing this out is because, like I said, this work that I'm going to be discussing about is to deal with geometry. And it is important to understand these unitary matrices, etc. You know that unitary matrices do a performer rotation. So that is the interest here. So again, this is pictorially what I am doing here. It gives you a better picture than what I discussed in the previous thing. Now, this mound of something that I have drawn is just a caricature again. It tells me the profile of the spin field at time 0. Okay, I've been using Z here. I put it as X. Just ignore that. So the spin profile at the time t is equal to 0 is given to me. Now, I am interested in how the spin profile will change in time. In order to do that, what I do is I bring in this imaginary torchlight, which is going to flash some light on this mound, and it's going to produce a scattered shadow somewhere. Okay. So the idea is that the shadow represents the profile of the spin that I'm looking at. Now, my interest is in finding out how the spin profile is going to change in time. Okay. And that is given by the Heisenberg equation. But if the spin profile changes in time, correspondingly the shadow on the wall, the scattered data, that will also change in time. So if you tell me how the scattered data is in time, then technically there is a way of going back and finding out how the profile is going to be. Now, okay, why do we take the circuitous route? That is because, like I pointed out in the previous one, these two are linear equations. Right? The psi z is equal to L into S, L into psi, that is a linear equation. And psi t is equal to M into psi, this is also a linear equation. And we have a better handle over linear equations than nonlinear equations. Whereas we pointed out that the spin equation, this is a nonlinear equation. So the way I'm dealing with my understanding how this spin profile changes in time is not by directly studying the nonlinear equation, but instead I keep track of how the scattered wave looks like in time. Okay. And what information do we have? We have some information from the boundary conditions typically, that at infinity, how does it behave, etc. Something will be available, and using that information one can find out. Now this is the picture, and there are several methods that are workable from this idea. One is the inverse scattering transform technique itself by Green, Gardner, Muir, and Kruskal. The one that I will be using is what one calls as a Darboux transformation, which I'll come to a little later. because, like I said, it is the geometry that I'm going to be investigating, and the geometry is better brought out by the double transformation method. I will explain. Now, my interest here is in not in finding how some arbitrary profile of spin evolves in time. I'm interested in finding out some simple solutions. Now, bear in mind that what I mean by this shadow is the scattered data. What does the scattered data consist of? A scattering means there are spectrum. And how do you characterize a spectrum? You tell me what are all the lines that are present and what is the amplitude of each line. So I might say red is there, blue is there, green is there. Then you have to tell me the intensity of what is red, intensity of red, intensity of blue, intensity of green, yellow, etc., etc. That is the data. So here, what I mean by this AK, 0, etc., etc., the K will typically stand for the frequency. This is a time t is equal to 0. And how does that amplitude change in time? That is what is my scattered data. And what is this A subscript K0 and what is A K of 0? Because my spectrum can be both continuous as well as discrete. So here I'm assuming that in general this has both a spectrum which is continuous as well as discrete. So the A subscript K0 means that there is a possibility of a discrete spectrum, and the A within brackets K comma 0 means that there is a possibility of a continuous spectrum also. Again, this is just a cartoon to indicate. Yeah. So now I'm interested in some specific solution. So I don't care what is the initial profile. I directly go to the scattered data. What I will assume is that there is some profile which gives me the simplest possible scattering data. And I ask, if that scattering data is going to evolve in time, what does the profile look like? So the simplest scattering data, what is my simplest scattering data? The simplest scattering data is a single line spectrum. So I am assuming that there is one line with frequency lambda naught. It has an amplitude A. Yeah, again, I'm writing it as a vector because this is a fictitious one. It typically has a vector as it lives in a vector space. So what I'm assuming directly is, instead of looking at the initial profile, I will assume that there is some initial profile that gives me a single line spectra. And how does that spectra evolve in time? And I ask, what is the inverse scattered profile associated with the single line spectra? Now that is a soliton. So the soliton is a special object for this reason in the scattering picture. It is the special profile that will give you only a single line in the spectrum. Again, keep in mind that I am talking about a fictitious wave. And a fictitious wave, that is the reason why this lambda is actually a complex quantity, because it is not real. You cannot ask me where this wave is and where do I see this wave. It is just a mathematical construct to help me with solving the problem. So again, the picture is that, what is a one soliton? One soliton is something that in the scattering problem produces a single line spectra. So in that way, it is very special. Okay. So this is my lambda, the complex plane. One soliton just simply is one point somewhere in this complex plane. Associated with that, there is an amplitude. A two soliton would be like there are two lines and there are two vectors associated with that, and so on. Okay, once again, to recall, what am I doing here? I have the Heisenberg Hamiltonian, which is given by this Hamiltonian with the condition that the spin is conserved. This leads to the continuous evolution equation, which is called as the Lando-Lipschitz equation. I spoke about the Lax pair, and the consistency of this wave equation now is equivalent to the Lando-Lipschitz equation that I'm trying to investigate. Okay. Now, what is this Darboux transformation? So we have converted this into a matrix problem. So S that I'm looking for is a matrix. It turns out that this S can be written as a unitary transformation of sigma 3, or I've written it as a sigma z, sigma 3, where the psi is going to be a unitary transformation. And like I said, it is a SU2 because it is a 2 by 2 matrix. It will have a determinant 1 and it is unitary. So you know what is a unitary matrix. So that geometrically it performs a rotation. Okay. So for example, I can have some simple S naught associated with psi naught. So associated with every psi naught psi that I'm thinking of, there is a S, because from this mapping I can get it. So here is one simple thing that I can work out. if you look back at this equation, you can see that S is equal to constant is already a solution. So you may be able to think of some simple solutions immediately. So one other solution that I have worked out here is or what we are starting with is like a helical ribbon. See that it is like a twisted one, and the boundary condition is matched because the extreme spins, they are in the parallel direction along the x direction. And yeah, I have taken it as AX. Don't worry about what notation I'm using there. So here is some of the x is taken as the axis direction. Okay. So this is one thing, is a simple solution which you can immediately guess, and associated with that there is a psi naught also that can also be found out. So geometrically what I mean here is, at some point I have the spin in some direction. The spin at the adjacent site is like rotated from this one. So what is responsible for that rotation? So I can, and that is this psi. So this psi is a function of x. That means if you tell me some point x, then that psi tells me how the spin at this site is rotated from the spin at some other site. So I can start with this as x is equal to 0. X is equal to 0, it is in some direction. At some other x value, I know that it is in some other direction, which is obtained by rotating from here. So slowly as I go from one end to the other, the spins are being rotated, and that rotation is accounted for by the unitary transmission. So that is what the unitary transmission accomplishes. It rotates my spin as I go along. So the entire profile of the spin is obtained from the psi. In this case, it is psi naught. But this technique of Darboux transmission, this is what it does. Once you have one such solution psi naught, one can find another operator called P. I mean, I have indicated as a P, such that P into psi naught gives you psi 1, such that my S1, which is another solution, can be written as psi 1 dagger sigma z psi 1 dagger. So it has the same structure like what I had here. Okay, you give me a certain psi, associated with that psi, I can find the corresponding spin configuration. There is a systematic way of finding that configuration, and that is the Darboux transmission technique. Now this P is called as a Darboux transmission. So the idea is that you give me one simple case, from that I can generate a P which will lead me to a slightly more complicated case. Now with psi 1, once again I can do another Darboux transmission, get a more complicated answer, and so on. So you can compare this with something you must have seen again in quantum mechanics, the harmonic oscillator, for example. You must have seen the ladder operator, the raising operator. The raising operator takes it from one quantum state to the adjacent quantum state, the next quantum state. So this is something like that. Here there was no soliton to start with, but the psi 1 could be a soliton. And then there is another Darboux transmission which will take it to a 2-soliton solution. Another Darboux transmission will take it to a 3-soliton solution, and so on. So it is the same way that your raising and lowering operators function. It is not that easy. Just a caution here. I am just conveying that the idea is the same as that of your ladder operator, because A dagger is the same for your entire system. Whether you go from n to n plus 1, or n could be 0, n could be 25, n could be 100. To the next level, if you want to go, all you want is this A dagger, which is the same operator, but here that is not the same. From 0 to 1, there is one Darboux transmission, but psi 1 to psi 2, it is another Darboux transmission. One has to systematically find it out. It gets progressively more complicated. But the idea is the same. The Darboux transmission is something that will take you from one soliton solution to another soliton solution, and it can be systematically constructed. So even though this has been put in a slightly different form, this method is exactly the same as the inverse scattering technique. It may not be apparent, but it is equivalent. Now, this is an exact solution for the Heisenberg ferromagnet that we've been discussing so far. What one calls as a rogue breather. Why is it called as a breather, and why is it called as a rogue? I'll explain. The rogue is explained here. The breather, because there is a certain periodicity to it. Rogue, because it has these characteristic features. So what we are seeing here is the energy density plotted as a function of x along one direction and time along the other direction. So far back in time, you find that the energy is uniformly distributed. You do not know what is happening. It appears to be the same everywhere. But as time progresses, you find that suddenly there is a strong excitation at some point, and then a little later it completely dies down without a trace. So you never know that such a strong excitation happened in that locality. So if you are somewhere here, for example, you would not even realize that something so strong has happened in your neighborhood. It is very local. So it is sudden, it is local and colossal. Sudden because in time, it is uniform everywhere, but suddenly it starts to pick up a strong excitation. It is local typically in both space as well as time, because you see it is in a small region where this huge excitation happens. Far away from it, you won't even notice it. It is colossal because the amplitude is also significantly large compared to the background. So after a little while, it completely dies down as though nothing has happened. So rogue waves were first observed in ocean. Some predictions are that this is what is responsible for things vanishing in the ocean, high seas like the Bermuda Triangle, and ships suddenly vanishing, etc. It could be because of this kind of rogue wave suddenly occurring. This have been observed also, and now there are other condensed matter systems where this is predicted or observed. Like for example, BEC, it is suggested that it will be there and we can observe it. There are several other systems where it is expected, it has been predicted or observed. Now, this does not truly bring about the interesting geometry that is happening there, because I am plotting the energy density here, not the spin itself. Okay, the spin I will show what is happening. This is a animation of animation, but it's an actual solution that is happening there. So you notice that this is a initial configuration that I started with. It looks like a ribbon, so the spin is like rotated or twisted. So at x is equal to 0, it is at the top. Then it slowly gets twisted with a uniform twist. At the middle, you again find that it is at the top. At the right extreme, once again, it is at the top. So it has gone through a twist of 4 pi. If you think of it as a ribbon, from 0, at the center, it has gone through a 2 pi rotation. Further down at the extreme, it has once again gone through another 2 pi. So totally, there is a 4 pi rotation that has happened here. But look at the animation carefully. So this is how the excitation proceeds. You find that the spins at the extremes, they do not change as expected because those are frozen. But in between, there is something interesting happened. I will explain. And it has come back once again to a state where it is twisted by 4 pi. But I'll play this once again. See if you can spot, but I am unable to stop this animation in the middle. Otherwise, I can stop it and show you. Actually, it goes through a stage where the total twist is 0. So in this region, for example, the total twist is 0. I'll show this with a clear picture next. Now, this is what I started with, which had a 4 pi rotation. Okay. And this is at the bottom is what you are seeing is the snapshot of what happened in the intermediate stage. Now you can see that the red line is connecting the top of the spins, and the blue line is connecting the bottom ends of the spin. Okay, the height of the spin itself does not matter because that is a scale that I have used. So you find that in the first one, or at time t is equal to 0 or towards the end, it was going through a uniform twist. There was a 4 pi twist involved. But here you see, for the first quarter, it is rotated about, let us say, in the clockwise direction. If you look at it down from the left end. And then after the first quarter, it goes into an anti-clockwise rotation. So for the half of it, it is going to be in anti-clockwise. And then later, it once again goes over to the clockwise rotation, so that actually there is no twist in this. So it is twisted in the clockwise direction, twisted in the anti-clockwise direction, once again in the clockwise direction. So the total twist is 0 as compared to what you are seeing here. Okay, I believe you are able to see this. Okay. Now this is called as a bell trick, which I will explain a bit. The curious thing to be kept in mind here is that this is possible from twist 2 or 4 pi to 0, only from 4 pi to 0. Had I started with something like 2 pi, this is not possible. That is the curious geometric aspect of it. So the ribbon that I showed, that you see in the top, that has been twisted 2 times to bring it to 0. Had I twisted it just once, it could not have been brought to a 0 state. That is the interesting aspect of it. Yeah, so this is what one calls as a bell trick. It's a video that I took from YouTube. I just search for a bell trick in Dirac's bell trick in YouTube. You'll find several videos that explain what this trick itself is, even though they may not go into the mathematical details of it. So what you are seeing is like a belt. Okay, once again, I'll play the animation. So what this guy is going to do is, this is going to be twisted once, twice. Now this is frozen at the middle. You see that this belt can be continuously brought to a state where there is no twist. Okay, I'll play this once again. Notice that the central portion, the block, is going to be rotated 2 times. So totally there is a 4 pi rotation. Don't worry about one half of it, just focus on the other half. You will notice that the belt at the left end and the right hand, once you make this rotation of 4 pi, after that it is frozen. But the left hand alone can be brought continuously to a state where there is no twist. Okay. So 1, 2 twist. So the left hand or right hand side is twisted by 4 pi. After that, nothing happens to the central portion. It is frozen. It has been continuously brought to a no twisting. The important aspect of this result, once again, is that you have to do it with twice 2 twists. You cannot do it with 2 pi. Okay, why that is so is the interesting connection. And to our knowledge, this is probably the only physical system which naturally exhibits the bell trick phenomena. I am not aware. I mean, after searching, I could not find out any other system with such a geometry where the bell trick could be seen in a natural fashion. So what I have done here is to illustrate this further. Since the boundary spins are anyway the same, so I just closed it. Okay, so it is now a loop. I just join the 2 edges. So this has actually gone through 2 4 pi rotation. So like earlier, the red line connects the top portions, the blue line connects the bottom portions. You notice that now the red one is a loop and the blue one is a loop, and the 2 loops are linked. Okay, you cannot simply take them out. And also, how many times are they linked? And that is obtained by the number of cuts and joins you have to make. So for example, at this point, I can make a cut, take it over to the other side and connect the blue ones once again. But even then you find that there is another link here. You could not do that. So I have to do one more cut somewhere, pass it over to the other side and then take it. So if I do it here, probably I'll have to do it here and bring it up. Only then I can remove it out. Otherwise, the 2 loops are linked twice. Okay, and the twice link is very important. So once again, I'll play the video. So at this stage, there is a twist which is 2, or a link which is 2. Now look at this video. Actually, they are not linked anymore. I can take out this red portion and the blue loop separately out. So the link or the twist is changing from 2 to 0 and then back to 2 in a discontinuous manner, because the twist is anyway integer. But the spins themselves, they are changing continuously, and that is the curious aspect of it. So this is a snapshots taken from different stages of the animation that I showed you. So at A, you find that the blue loop and the red loop, they are linked twice. But look at C, the blue loop and the red loop, they are not linked anymore. So if you forget about the spins and just look at the loops alone, I can simply take them out without any cutting or joining. Whereas here I cannot do that. They are linked twice. And that is what is shown by the link calculation here. If you plotted as a function of time, you will find that initially the link was 2, the number of links that between the blue and the red ones is 2, and suddenly at some point it changes to 0, like here there is an intermediate region, and then once again it suddenly goes back to 2. Now here again the curious aspect, which is the same as in the case of twist, is that the link 2 to 0 are connected. You cannot take it from 1 to 0, that is impossible. Again, bear in mind that the link may be changing discontinuously, but the spin itself, that is adjacent spins, if you look at, they are always continuously changing, which means two adjacent spins will be varying only by a small amount. They won't be varying in a huge way. Yeah, now I will explain what is happening, and that is the intriguing geometry that I was talking about. So you must be familiar with what is called as an So3 rotation, which is just the rotation in 3 dimensions. And the rotation in 3 dimensions is represented by an orthogonal matrix. And an orthogonal matrix can be represented as a exponential of n is a unit vector, j is your j1, j2, j3, your angular momentum matrices, okay? And theta is the angle of rotation. So what this actually stands for is there is a rotation happening about the n direction by an angle theta, then that can be represented by e to the power n dot j into theta, and that will give you this SO3 matrix. So this theta will go from 0 to pi, because once it goes to pi, you find that it's once again repeating the same values. So the range of this theta is from 0 to 2 pi. So this is how I'm going to represent this in a geometric manner, what one calls as an SO3 manifold. Each of these orthogonal matrix is characterized by n and theta. So you give me one n and theta, I can write a corresponding orthogonal matrix. So I will write it as a vector quantity r, and the r is given as magnitude theta in the direction n. So once you tell me n and theta, unit vector n and a theta n, I will construct an r vector which has a magnitude theta and a direction n, and plot it in a sphere like this. So for example, you give me n, so along that direction, I'm going to write a line, and theta you have given me, so the magnitude of this line is going to be theta. So as theta goes from 0 to and keep on increasing in the n direction, so it is going to go along this line. This vector will keep on increasing. It reaches a point here which is pi, but then there is something curious, because if you think about a rotation about, say, the z direction by an angle pi plus theta, it's the same as rotation about the minus z direction by pi minus theta. Okay, because you could have taken a anti-clockwise. So for example, a clockwise rotation, you can take up to pi plus theta, but that is the same as an anti-clockwise rotation by pi minus theta. So if I want to represent each of these orthogonal matrices in the sphere, you find that once I go to pi, this pi is automatically now connected here. Okay, so this point is same as this point. So what I'm trying to do is I'm trying to represent each of these orthogonal matrix in a sphere. So every location in the sphere, inside, outside, on the sphere, sorry, not outside, inside and on the sphere, each point will correspond to an orthogonal matrix. Because if you give me some arbitrary point, I can look at the corresponding, I can look at the corresponding distance from the center, I can look at the corresponding direction. So that has given me my theta and n, I can construct my corresponding theta. So every orthogonal matrix there is can be represented in this sphere. So theta is equal to 0 will be the central point. Theta is equal to pi is on the sphere, but theta is equal to pi is same as this opposite point. So if I further increase my rotation, the corresponding matrix will go along this line till theta is equal to 2 pi, which is at the center. But theta is equal to 0 and theta is equal to 2 pi are the same. So it comes once again. So now I can think of a matrix associated with every point on this manifold. Okay, you give me a point on this manifold, I can find out what is the corresponding n vector, I can ask what is the corresponding theta vector, go to this expression, and I can tell what is the corresponding rotation matrix. Okay. Now I will come again. But I told you that The unitary matrices that I am dealing with in my Darboux transformation, those were SU2 matrices. Okay, these are 2 by 2 matrices, unitary matrices with a modulus 1. The overall phase is not important. But a SU2 matrix can be represented in this manner: e to the power minus I n dot sigma theta by 2. Now this theta by 2 is very crucial. Okay, this is again something you should be familiar with in quantum mechanics, right? Where you can also write this as cos theta by 2 into identity minus I into n dot sigma into sin theta by 2. But the curious thing now here is that this theta has a period 4 pi. Because you see, as theta is equal to 0, this is identity, this part will be 0. At theta is equal to 2 pi, this becomes cos pi, this part again becomes 0, but cos pi is minus 1. So you started with identity, at theta is equal to 2 pi, it becomes minus identity. At theta is equal to 4 pi only, it comes back to identity. So the period that we are talking about here is actually 4 pi, not 2 pi. And this is the first piece in the puzzle. Why is it that in my bell trick, we are connecting 4 pi with 0, not 2 pi with 0? Yeah. So once again, I'm going to follow the same trick and construct the manifold associated with SU2. A unitary matrix now is given by this n and theta. You tell me what is n and theta, I can go to this formula, construct what is the corresponding matrix. So I'm using the same trick here. Associated with every u, I will write a vector r, has a direction n, has a magnitude theta, plotted once again. Okay. Now here once again it is the same trick. Theta is equal to 0 this point, theta is equal to pi is this point, theta is equal to pi comes here, which is the same point here. Now theta is equal to 2 pi, but then my period is 4 pi. So at this theta is equal to pi, what I have come across is not the same matrix, but minus times the same matrix. So if theta is equal to 0, I had a matrix. The matrix at theta is equal to 2 pi will be the same matrix multiplied by a minus sign. It is not the same matrix. So there is an overall phase that is added throughout. So this is 3 pi. 3 pi is back here, and 4 pi is at the center. So you find that in the case of SO3, we had just one trip from 0 to pi to 2 pi. But for SU2, I have to do this trip twice before I come back to identity. So my SU2 matrix, once again, I'm repeating here, is expressed as a e to the power minus I n sigma dot theta by 2. It has a period 0 to pi. And you see that this is crucial, but I will not spend much time in this. The sigma matrices obey this commutation relation, which is something that you are already familiar with. But a reminder, because I'm going to compare this with the SU3 case. In the SO3 case, it is e to the power n dot j into sigma, where j1, j2 or ji, jj will again obey the same commutation relation as what we have here. The difference is that in the case of SU2, your period was 4 pi, whereas in the case of SO3, the period is only 2 pi. So this is the difference. In the case of SO3, the entire set of matrices that I can write associated with one particular direction will be just this line. You tell me any point in this that corresponds to a certain theta, and all those will correspond to possible rotations about the n direction. But when it comes to SU2, the picture may not be very clear here. Actually, there are two lines. There is a red and a blue line. So you may be starting from the 0 along the blue line. You go to this point, come here, it is still the blue line. Once you come here, it starts along the red line because there is a phase that has changed. You go to the red line, and once you come back, only then you are going to connect to the blue line. So this is what one calls as a double cover of SO3. Okay. So associated with every SO3 matrix, there are two SU2 matrices. So SU2 matrices are double in number compared to SO3. And what it also means is that this is not simply connected, meaning SO3 is not simply connected, whereas this is simply connected. What one means by that is, suppose I have this thing, there is no way I can bring it to 0. I can compress this as a loop and bring it to 0, because if I move this point, this will also move this point. So if I have a set of matrices, okay, that are associated with some curve on this thing going from one point to another, there is no way that can be shrunk to a 0, whereas you can do that in the case of SU2. That was the maneuver that happened. So what I have done here is I have already found out this SU2 matrix, right, associated with the Dabo transformation, which is basically my spin configuration. So that entire spin configuration was SU2, a set of psi matrices, function of Z, going from one end to the other end. What I have done here is the corresponding manifold plot. So associated with every psi there is a point in this manifold, and that plot is what I have done here. So at time t is equal to 0, this was a helix, and that there are actually two lines here. There is a red dot here and there is a red dot here. There is also a yellow dot here and there is another yellow dot on the other end. Okay, so it starts from a red dot, goes over to a yellow dot. I'll show you. And then from the yellow dot, it goes to the yellow dot and then connects to the red dot. So there are actually two lines. The video will make it, the animation will make it clear. This is how it looks like in the manifold. So you see that there is a red here. The opposite end is here. The red here, there is an opposite end here. So now you see in the process they have actually connected. This loop can be shrunk to a point. That is not possible in the case of SO3. And that is the reason why you cannot go from 2 pi to 0, but you can go from 4 pi to 0. Yeah, in a short period, it is actually difficult to understand this, but if you think about it, it is all the explanation is here. In the case of SO3, if I have some curve, what does that curve mean? That curve starting from one point at one end to another point at the other end, what does that curve mean? The curve stands for a whole set of SO3 matrices. Okay, but that set cannot be shrunk to a point, because as this point moves, this point will also move. So there is always this curve which is going from one end to the other end. You cannot get it out of there. Whereas in this case, you find that this yellow on one end is connected to the red on the other side, and this red is exactly opposite to the other one, but this can be shrunk, and this kind of shrinking happens. Now, in my system, what we have done is we have not brought in dissipation, for example. But if the system also has dissipation, what will happen is that slowly it will shrink to a point which is 0, which corresponds to all the spins being in a uniform direction. So the summary of why that bell trick happens is that in the case of So3 rotations, it is not possible to bring this, any curve for that matter, to a closed loop. Whereas in the case of SU2, it is possible to connect a loop of this nature to 0. What does that mean? Here the total period was 2 pi. 2 pi cannot be shrunk to 0. If it is a single point, it corresponds to a twist being 0. 2 lines means that the total twist it has gone through is 4 pi. So in the case of SU2, 4 pi can be shrunk to a point, whereas in the case of SO3, it cannot be done. That was the reason why the bell trick happens there. Now, these are snapshots of what happened here. So you see, initially there were 2 lines, which is not very apparent here. As the spin mode, the rogue breather, excitation starts to happen. It goes like 2 distinct ones, but actually there is a red one here and the corresponding red one at the other end. There is a yellow one here and there is another yellow one here. So it is like you are starting at some point. There is a sequence of matrices. It comes to this red end, then it automatically goes over to the other end, which is in the opposite direction, diametrically opposite. Then it goes along this direction, comes to red, comes to yellow, and once this yellow is there, it's the same as this one. So that is how. So even though it looks like 2 curves that are disconnected, they are actually joined, because this red point is same as this red point, and this yellow point is same as this yellow point. So in that sense, it is connected. And as the evolution happens, you find that this red and yellow can be brought together. It is only yellow and yellow that cannot come close to, because they are diametrically opposite points. the red and yellow can be brought close together, and you find that they shrink to the same point. So when this red and yellow comes to the same point, this red and yellow will also come to the same point in the diametrically opposite point here. It has come to a closed loop. So like I said, in our system, we do not have a dissipation. But if there is dissipation, then what will happen is that beyond this point, this thing will slowly shrink to 0. And 0 means that all the spins in my spin chain will be along the same direction. Now, why it does not happen in our present system is because there is a energy conservation and there is also a total spin conservation. I'll go back to the picture to illustrate that. So, for example, this configuration has a total spin 0. This also has a total spin 0. But this ribbon is not the same as having a uniform spin everywhere. Whereas this one can be brought to a uniform spin everywhere. A uniform spin everywhere means that the total energy is 0, but this one cannot be brought to that case. So once the spin configuration has come to this, if I put in some dissipation, what will happen is that on account of dissipation, all the spins will go to the minimum energy state, and minimum energy state is where all the spins are in the same direction. So the way this spin configuration goes over to a configuration where all the spins are in the uniform direction is, first there is this change in twist happening from twist t equal to 2 to t equal to 0. And after that, all the spins can go in the same direction provided a dissipation or damping is there. There is also another interesting way to look at this. The spin is a unit vector, right? So what I have done is I have plotted all the unit vectors on the sphere. So, for example, this is a center. Okay. This is a center, and this is a point on the. So this can be, okay, I'm unable to draw the line clearly using mouse, but imagine that this is a straight line. So this is one spin vector. The adjacent spin vector is like this. Sorry, it's not giving me a straight line. And the next spin is like this. So basically all the spins have been plotted here, right? So each point on this curve corresponds to a spin orientation. Now, this is what one calls as an indicatrix. It tells me how the spin is changing. If I bring in all the spins to all the base of the spins to one point, then it will form some curve on the sphere. Now, initially what I started with was a helix. And what is a helix? Helix is the spin taking a circular twist. And I told you that there were 2 twists that was involved. So that is the reason why it is like a twisting twice, going back to the same thing. Now, this is an animation. Okay. Okay, the animation doesn't work. Okay. I don't know why. Okay, I will tell about the result here. Now, what is the area associated with this loop? See, this is a closed curve on a surface. So the area is a vector quantity. So for example, associated with this closed curve, I can think of this area on the hemisphere as the area associated with this curve. Now that depends on, there is an associated direction also, because as z varies, this vector is going to have some direction. Okay. So it is like the spin vectors are changing along this direction and then going along this direction. Okay. So what is the area that is associated with this loop? This loop will have an area that is this part of the hemisphere. Okay. Because it has a direction, so you use the right hand rule to tell what is the area associated with this loop. And similarly, the remaining part of this loop, that has an area that is this larger hemispherical thing. But that, because of the symmetry in this, is exactly the same as the remaining part of the sphere. So if I add the two areas, it happens to be the total area of the sphere, which remains a constant. There is a clearer way of explaining this. So what is the area traced by the closed thing? It is S dot dA. dA is the area on the sphere, on the surface of the sphere. And at every point I told you that the spin is like a directed in the direction. My dA is a small patch on the surface. So at every point I'm calculating what is the spin and finding out the area that is associated with it. Sorry. Right. So this is the area that I'm trying to calculate. This has a very similar feeling from magnetism that we have studied. So I can write this using Stokes theorem as A dot dl, where A is like the curl of A, is associated with the spin vector. So S is a radially outward vector, a normal vector. So this is like asking for a vector potential that is associated with a radially outward magnetic field. So our magnetic field is not radially outward normally, but what is the magnetic field that is associated with that is a radially outward magnetic field? That is what you will get for a magnetic field of a monopole. Okay. If I were to have a magnetic monopole, the monopole will have a radially outward magnetic field. So this is like asking for the flux due to a magnetic field that is produced by a monopole. And for the monopole, one has the expression for a vector potential. You can easily look up some textbooks. And if I go by the usual notation that if I can write my S as the polarity composition, then this area can be written in this form in terms of phi and right. So I just have to substitute for A dl. So if I take it along the closed loop, I can calculate what is the area here. And interestingly, this is actually the momentum associated with the spin field. Again, this connection I'm not showing, I'm just leaving it as a statement. This quantity is actually the momentum of total momentum of the spin magnetic field. And that is actually a conserved quantity, and that is related to the wreath. Wreath is just like link and twist is there. There is another wreath which I did not explain, but we can leave it at that. Yeah, and what one sees here is that the total momentum is actually a constant, and it is known to be a constant for the Heisenberg magnetism, Heisenberg Hamiltonian. Yeah, so what we have seen here is a geometric relation of what one calls as the momentum of the spin chain. There is an energy bound. I am not showing how I get this energy bound, but depending on whether the total twist is either odd or even, one can show that the energy will have a minimum value. I have already shown that in the case of even twist, the minimum value is 0, because for an even twist, the total twist could be 0 also. If the total twist is 0, then it is possible that all the spins are along the same direction, that is parallel direction, in which case the total energy is 0. Whereas if I have a total twist which is 1, it is not possible that all of them are in the same direction. So it has an energy bound, and the energy bound is like 4 pi square by L. So what this means is that if I start with some total twist n, then it can continuously go to n minus 2 and n minus 4 and so on in the presence of dissipation. And finally, it will settle down to either n is equal to 1 or n is equal to 0, depending on the n that I started with is either odd or even. So one can see that there is an energy gap at the lower level. It means that there are now two distinct topological sectors depending on what is the total twist in my spin chain. If the total twist is even, then all the continuous transitions will go only from even to even. It can go from 4 to 2, 2 to 0, or any higher depending on how much energy we are giving. Or if it is odd to start with, then it can only go for odd spins like 5 to 3 to 1. Below that it cannot go, and there is an energy bound that distinguishes the two sectors. We have been trying to think of applications. I mean, applications can be thought of, but working it out is proving to be difficult. So what one can easily try to think of is, again, in terms of memory applications. I can I can think of these two as two different memory states. So for example, in this case, the total spin is 0, but the energy is really high. Now here again, the total spin is 0, but this can be continuously brought to a state where the energy is 0. Because if I put on dissipation, automatically the spins will all go to the parallel direction. So now I have two states which can be distinguished either by the total spin value or total energy value. So reading and writing, if I manage to accomplish it, then I have a proposal for a spin chain that can be used as a memory, which is what we are currently engaged in. So I understand some portions of what I talked about may be a little difficult to digest if you are listening for the first time, but I believe I have conveyed interesting geometric aspect of the spin chain that we have investigated, especially for the rogue breather. So I will, this summarizes what I wanted to speak. I will stop here, and if there are any questions, I'll be happy to answer. Thank you.
Thank you, Murugesh. It is time for questions.
Thank you very much, Murugesh, for a very interesting presentation.
Thank you, sir.
Really enjoyable. So the two kinds of breathers you are talking about, for example, in this slide, so they correspond to, the first one corresponds to magnetic spin waves, I suppose, of a finite number of waves, I think, for two waves, the standard the spin waves. So that you try to interpret in terms of the topological quantities. And the second one is just the deformation of the spin waves as a rogue wave. So do they have anything to do with solitons, or?
Yes, sir. Actually, yes, sir. Shall I?
Yeah.
So I don't know why my animation does not work, probably. So actually, these two are the same excitation. So the breather excitation, I have not explained why I call this as the rogue.
So what you call a breather is essentially spin waves.
Yeah, actually, it is a soliton with a specific boundary condition.
Soliton with a.
So, for example, in the usual soliton, what we take is that the spin goes to a uniform one at the ends.
Yeah.
At infinity. What I have here is that it's a periodic boundary condition. So I have a finite length spin chain.
This looks like the spin waves we have given with Roy-Grach and C. Johnson, I suppose. Isn't it so?
No, this configuration looks like a spin wave, but it is not actually a spin wave. The two figures that you are seeing, they are the same excitation. This is a snapshot from an intermediate stage. When initially it started with 4-pi twist in it, but suddenly at some point it goes over to a 0 twist in it. So there is an interesting maneuver that is happening in the process of this excitation. So the spin wave initially started like a ribbon, but then it changes in time, suddenly goes over to the second configuration that I'm showing here, where the total twist is 0, and then it once again goes back to the previous one.
Okay.
So there is this topological change happening in the process of this excitation. So the rogue breather, this picture, the energy picture does not show that. But when this excitation happens, there is an interesting geometric feature that is happening there, which is what we have shown. So at this point, for example, it looks like a ribbon at the far away, far back. At the far ahead, at t is equal to 4 and beyond also, it looks like a ribbon. twisted, uniformly twisted ribbon. But in the intermediate range where the rogue breather happens, that is when we have the second picture. So it is one continuous excitation which takes it through this process.
Oh, okay. So all these occur only for isotropic chain, or do you have similar structure for anisotropic? Also?
Anisotropic we have not investigated so far. What we were trying to do is, in this itself, we were trying to think of an application, and that is proving difficult, the numerics. We tried with kind of interactions, because what we are really trying to do is, dissipation is critical, but dissipation is not something I can tune. I am trying to think of an interaction or some perturbation to the Hamiltonian that will act like a perturbation, act like a dissipation, but something that I can control from outside. Because dissipation will put me in a uniform state, but after that I have no handle over it. I cannot bring it back to the old state. This picture has been shown in the absence of dissipation.
Yeah, but isotropic case, from application point of view, will be too idealistic.
Yes, sir, I agree. In fact, the Heisenberg model that we are looking at is a toy model, truly speaking, because there are so many effects that we are ignoring. Yeah. We have to introduce all that to study the realistic case.
Yeah. Okay, then. Thank you very much. Thank you.
Yes, sir, thank you.
So, any other question from students? Murugesh, what is the seed solution you consider in the turbo transformation?
Seed solution, this is the seed solution, sir. S naught is equal to, this is a seed solution. So the seed is something that satisfies the boundary condition. The K naught has to be properly chosen. We have chosen K naught in such a way that there are two twists in it. Okay. If you do that, then you go by the Darboux transformation or any of the other methods. Yeah, any method will work, because basically this is IST. It will give you a breather solution.
You stopped at first iteration, or you've gone to second and third?
The second, actually, I think it is available. In fact, ML sir and students have also done in the case of solitons, the NLS equation. But from there also one can get this by means of the gaze transformation we can make use of. But we focused more on the geometry once we recognize that there is something interesting that is happening there. And this was our major focus.
So is it possible to give interpretation in terms of knot theory?
The problem is, actually there is another solution which actually produces a knot. I have not discussed this today. If you relax, if you change the boundary condition differently, so here, for example, I have taken a finite domain, a finite spin chain with boundary conditions which are periodic. If you relax that condition and try to do something similar, what happens is that you have the, corresponding to the soliton, one can draw a curve in 3D, and that curve actually shows a knot. So we tried to see what this knot actually means in some experimentally measurable way, but we don't have an answer for that either.
Thank you, Murugesh. So, questions? Okay, Murugesh. Since I'm not seeing any questions,
yes, sir.
I would like to conclude the session by thanking Professor Murugesh for accepting our invitation and giving a very wonderful lecture. Okay. Thank you once again, Professor Murugesh.
Yes, sir. Thank you for the opportunity. Hope I can give another talk sometime future.
Yeah, sure. Please visit us sometime.
Yes. Yeah. It has been a long time since I visited there.
Yes.
I would like to visit again.
Okay. I will write to you other formalities by email.
Yes, sir. Thank you, sir.
Thank you.